Hello, this is Math 2231 coming to you from the College of DuPage for the summer of 2020, and this lecture is entitled Linear Approximations, Differentials. And at this website that I'm pointing at right here, there's a very nice animation, and the animation shows many things, but the big thing that I want to talk about here is the animation shows that if I'm far away from the picture, what happens is the purple curve and the blue curve are quite different. And the blue curve is the tangent to the purple curve at this point. But when I zoom in closer and closer and closer, what happens is the difference between the tangent line and the purple curve fundamentally vanish. This suggests that near a specific point of interest, the point of tangency, there's not a big difference between the function and the tangent line. This fact is often exploited in math and science work and motivates the following definition. So if f is differentiable at x equal a, then this line L of x equal f at a, the point of interest, plus f prime at a times x minus a. This is the point slope form of the equation for the line. It's called the linearization of f at a. And they're close to each other. This means approximately equal to. F of x is approximated by L of x. And so that is the standard linear approximation. Here's a problem I'm asking you to do. We're to determine the linear approximation for y equal f of x is equal to the cube root of x, that's the function, at the point x equal 8, that's the point of interest. And by the way, x equal 8 is a good point to use because we know what the cube root of 8 is. It is 2. But then, after we find that, we're to use the linear approximation to approximate the value of the cube root of 8.05 and the cube root of 25. You know what to do? Let's see how you did. Alright, so we need to find the slope, so we're going to take the derivative of y equal f of x equal x to the 1/3. So the derivative is going to be 1/3 x to the minus 2/3, which can be written this way. And we want to be at the point is going to be x is 8. And if I plug x equal 8 into this equation, I know that I have 2. So the value is 2. And also the slope, f prime at 8, is found by substituting 8 into this derivative. Now, 8 squared is 64, and the cube root of 64 is 4. And so what I have is 3 times 4 in the denominator, so the slope is 1/12. So the linear approximation is L of x equals 2, that is f at our point of interest, plus 1/12, that is the slope, times x minus 8, and that can be simplified into this slope-intercept form. Now, the second part of the problem says, let's plug in 8.5 into both L of x and the cube root of x, and you see I get almost exactly the same number. Now that shouldn't surprise you, because if I look at this curve over here, you see L of x is blue and the cube root of x is the red, and near 8 and 8.05 is certainly near 8. There's not much difference between those two at all. But if I go all the way out to 25, which is way out here, there is a gap between these two functions, and if you check, you see that L is 3.5 and the cube root of this is less than 3, and so there is a gap. So you see, the closer you are, the better the approximation. And this happens a lot in your math and science and economics courses. They will have an expression like the square root of 1 plus x, and we'll say, yeah, but that's pretty close to this line, and lines are easy to deal with. Or this function is hard to deal with, but it's pretty close to this one. Or this one, that is even more complicated, is pretty close to this one. So that is what will happen as approximations in many of your classes. Let's do another example. We're to determine the linear approximation of sine theta at theta equals 0. You know what to do. Let's see how you did. Okay, so f of theta is sine theta, and when I put 0 in, I get f of 0 is 0. The derivative of the sine of theta is the cosine of theta, and when I put 0 in there, I get 1. So that means the slope is 1, and the point is 0, 0. So L of theta is going to be f of 0, which is 0, and this is going to be 1 times theta minus 0. So I just get theta. And so what this says is that the sine of theta, which we were approximating, is approximately equal to theta. And you see that makes sense because sine of theta over theta, the limit as theta goes to 0 is 1. Now, this is actually an important linear approximation. In science, optics, this approximation is often used to simplify formulas. It's also used to help describe the motion of the pendulum. And here's a pendulum, and this pendulum is moving through a small angle, so it's going back and forth and back and forth and back and forth. The actual differential equation that governs this, if you use the science, is the second derivative of theta with respect to t plus g, the acceleration of gravity, over L, the length of the pendulum, times sine of theta is equal to 0. This is a very nasty equation to solve because it is nonlinear. But if we say, oh, but the sine of theta for small angles of theta is approximately theta, I will change it into this problem, which turns out in differential equations to be a much simpler problem. I'll see you in 22.1. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. God bless.